What does the universe is not locally real mean? This year's Nobel Prize in Physics was given for proving it. Can someone explain the whole concept in simple words? Hi, you, Kabir 9966. Quantum entanglement is a phenomenon, in which the measurement results of two entangled particles are correlated. I.e., if I measure the spin of 100 pairwise entangled particles along the same axis, the results of the entangled pairs will always correlate. In other words, when one measurement gives spin up, measuring the other will always give spin down. This holds true, no matter how far the two particles are apart, or how short the time between the two measurements is. One possible explanation of this phenomenon goes as follows. The measurement results follow a secret plan that is created together with the entangled pair. That is, the measurement results are deterministic. You can imagine this like hiding a small item in one of two identical boxes. Then you take one of the boxes to the moon and open it. If you find the item, you instantly know that the other box is empty. This would be a very neat solution, as no signal would have to be exchanged for you to gain this information, thereby sidestepping the problem of relativity. Furthermore, this theory is realist, in the sense that the state of each object is well defined at all times. This is called a local hidden variable theory. Here, the term local signifies that this theory holds on to the constraints of relativity. Any object can only influence its immediate surroundings. This constraint is also called locality. The idea of this theory is that the measurement result of all quantum mechanical particles is predetermined from the moment of their creation in such a way that conservation laws are respected. When we measure one particle of an entangled pair, we get the secretly predetermined measurement result, and thereby instantly know the state of the other particle, without the need for any signal to be exchanged between them. As it turns out, we can test whether or not such local hidden variables exist using the Bell inequalities. Veritasium has made a pretty good explainer how this test works. The bottom line is that such a hidden variable theory would lead to different outcomes than what we measure. Consequently, the local realist theory described above cannot be true. We have to let go of at least one of these constraints. The universe can respect realism, but not locality, or it could respect locality, but not realism, or it could respect neither. A theory that respects locality but gives up local realism would mean quantum states really remain in an undetermined state of superposition until they are measured, and in the moment of the measurement, the wave function of both particles instantaneously collapses, according to the Copenhagen interpretation anyway. There are no hidden variables predetermining the outcome of these measurements, and no signal is exchanged faster than light. The Nobel Prize was given for experimental evidence that realism does not hold locally. It means that it is impossible for our universe to be both local and real, one or both of those properties must be false. It means that either there are interactions at a distance in our universe or that the underlying foundations of our universe behave in a very exotic and strange way, taking actual form only when indeed interacting with anything. Local means here that all interactions take place in the direct spatial and temporal neighborhoods. While the temporal part is intuitive for us, the spatial one is not. We are used to perceiving and even manipulating things at a distance. But this is all an illusion. We see only photons that reach our eyes, and we use electromagnetic radiation to transfer sound to our wireless headphones. And from what we know so far, our universe is entirely local, as we know not a single action at a distance. Even famous quantum entanglement is an inherently local phenomenon because for the entanglement itself to happen, both particles must be in a direct neighborhood. Real means here that all quantum objects indeed have specific properties since the moment of their creation, just like we are used to perceiving the world. To simplify a lot, whether they are hard or soft. In touch is defined at the very moment when they were created. If they were non-real instead, whether they are hard or soft would be determined only when you actually touch them, long after their creation. In other words, to answer if our universe is real is to answer if we perceive quantum world behavior in a probabilistic way because it is inherently probabilistic, non-real universe, or because we lack some kind of knowledge about the measured object, real universe. It's important to note here that there is no such thing as passive observation, measurement in the quantum world. You can't just sit idly by and watch quantum objects behave. You have to actually touch them, to actually interact with them, altering their state. That said, it's also important to state that we don't know which of those properties is actually false or even if both are false. We only know that they can't simultaneously be true. Quantum mechanics is an inherently statistical theory. When you observe a quantum object, the theory tells you the probability of obtaining a result, but there is always an element of randomness to it, e.g. the cat has a chance of being alive and a chance of being dead. This has led some people to wonder if quantum mechanics is an incomplete theory, a statistical tool that fails to discover the real properties of objects. If it is, there has to be some hidden information that it just can't access. Was the cat really alive or dead before I observed it? Or was it really neither, and did it only gain a definite state due to the observation? The experiments showing Bell's inequalities to be true proved that there cannot be locally hidden information, meaning that there is no such thing as a true hidden property of the particle that you discover with a measurement. Reality is inherently random, and the measurement forces the particle to adopt a state that it did not have in any sense prior to the measurement. Yes, the cat was in fact neither alive nor dead, it's not that we just couldn't know. Edit. The cat is kind of a nonsense example because yes, the cat would know. It's not a quantum object, and its properties have been defined through interaction with other things, the air around it, the box, etc. But it's a good proxy to talk about particle spins, for instance. Edit 2. In this context, measurement really means any exchange in information, meaning any time the measured object interacts with something else.